I'm going to try to remember to unhit record when we go to break because I didn't last week, and it means y'all wound up with a pretty long video, which, you know, you can always fast forward through parts of that, but try to break them up by, you know, before break and after break. So there's 2 videos and each of them isn't so long. Okay, so last week we looked at how to add, subtract, and multiply complex numbers. Tonight we're going to look at how to divide complex numbers. We're going to do just a couple of problems, and then we're going to move on into chapter 1, section 5. So when you divide, so this is a division problem. It's the complex number, in fact, the imaginary number 4i, divided by the complex number 2 plus 3i. And so if you kind of remember on the addition, subtraction, and multiplication, we sort of already had a little bit of intuition about how to do that. You know, like adding and subtracting was like combining like terms, and multiplying was like distributing, you know. Division is a little bit different in that on the surface of it, it doesn't seem like there's a good sort of model in our heads for how to do division. I mean, if I were to, let's just say, for instance, that I did something like, you know, I'm looking at this problem and I'm thinking, okay, well, what do I know about division? Let me zoom in a little bit here. And I'm just thinking, what do I know about division already that maybe I could apply to something like this? Well, I mean, I don't know. When we first learned to do long division, we write it like this. But if I write it like that, I don't know what to do with that either. Oh, there's Michaela. Okay. So I think that makes us complete here tonight because I know Richard's not coming. Okay. I'm sorry. Oh, that's okay. So anyway, I don't know what to do with this, you know. So we just don't really have a good intuition. It's because we do have a little bit of an intuition, but it's not probably what you're thinking about. It's got more to do with how we deal with fractions. So for example, if I did this, this is the fraction 6/8. But remember, the fraction bar also could be treated as a division symbol. Well, when I look at 6/8, does everybody agree that that when you see this, the first thing you want to do is simplify it, right? And we recognize that there's a common factor of 2 on top and bottom. And so I could say that 2 goes into 6 3 times and 2 goes into 8 4 times. And so we would say that 6/8 is equal to 3/4. And we would say that we've simplified this fraction, right? And that's true, we have. But it turns out we've also done a division problem. Like 6 divided by 8 is literally 3/4. That is 6 divided by 8. And we can prove it because remember we talked about, I think when we were talking about how to know what happens when you're dividing by 0, if this statement is true, if 6 divided by 8 is really equal to 3/4, we could check and see if that's true, because all we'd need to do is check to see if our divisor 8 multiplied times our quotient, the answer we get when we do a division problem, in this case 3/4. If we multiply these and get our original dividend 6, then 3/4 is definitely the correct answer to 6 divided by 8. And of course we will, because when you multiply these, you get 24/4, which is 6, or you could say 4 goes into 4 one time, 4 goes into 8 2 times, 2 times 3 is 6. That's what it's supposed to be. So when I say that 6/8 is equal to 3/4, I've also done a division problem, but it doesn't really feel like us. It doesn't really feel to us like we've done division. Do y'all agree? It feels like we've simplified a fraction. Well, that's kind of what this is like, sort of, in that I'm going to tell you a rule and say that you can't call this thing simplified until you've done this. We're going to do that. We're going to apply that rule. We're going to put it in this form that I say it has to be in to call it simplified. And once we do, you're going to think, okay, well, we simplified this hideous looking thing using this dumb rule that Norris told us to use. And you will have done that, but you also, it turns out, will have done a division problem. So here's the rule. Anytime you have a division problem involving complex non-real numbers, you have to find a way to write this so that you do not have I in the denominator. It's okay to have I on top, but you can't have it on bottom, okay? And here's the little trick we're going to use to make that happen, and it's a pretty simple one. Remember how when you have a fraction, so a minute ago we showed that 6/8 simplifies to 3/4. But do you agree if I wanted to, I could also go the other way and say that I have 3/4. Well, if I multiply that times, for instance, 2/2, if I do that multiplication, 3 times 2 is 6 over 4 times 2 is 8, I get 6/8. But what that shows is that 3/4 is the same number as 6/8, right? Because 2/2 is just 1. I've just changed the way it looks. By the way, I've changed the way it looks in this sense, that if we had, going back to the old pizza problem, if we had 3 out of 4 slices of a pizza, 3/4 of a pizza, and I sliced everything again, now I've got 6/8 of the pizza, but that's still just 3/4 of the pizza, right? So remember, if you have a fraction, you can always multiply it times some number over itself, as long as it's not 0/0, which is undefined. You can always multiply that fraction times a number over itself because that's just 1. And it doesn't change the value of this number 3/4. So we're going to do something similar to that. Remember, what we want is we need to write this so that we don't have I in the denominator. And what we did at the very end of class last week gives us a hint as to how we could do that. What if I multiplied this denominator 2 plus 3i times its complex conjugate, which is 2 minus 3i? Remember, we saw last week that if you have two complex numbers and they're exactly the same, except the sign of the imaginary part is opposite in both numbers. So I got 2 plus 3i. Here's its complex conjugate, 2 minus 3i. Remember, what we found is when you multiply these, you actually just get a real number, right? And also remember, we saw there was a shortcut for doing that. You could FOIL it all out if you want to, distribute it. But we saw that there was a shortcut, which is you can square the first number, 2 squared is 4. You can square the second number, 3 squared is 9, and you can add them together, and that's literally the answer you're going to get if you did do the full scale multiplication of these. So if we multiply the 2 plus 3i on bottom times 2 minus 3i, its complex conjugate, we just get 4 plus 9, which is 13. And we don't have I in the denominator, right? But if you multiply this denominator times 2 minus 3i, then you also have to multiply this numerator times 2 minus 3i. Everybody see that? And of course, it doesn't matter what 2 minus 3i is. If it's divided by itself, that's just 1. Well, when I multiply on top, I'm just going to distribute. So 4i times 2 is 8i, positive 8i. And 4i times negative 3i is positive 12. And if you don't remember the little trick there, remember when I do 4i times negative 3i, 4 times negative 3 is negative 12. I times I is I squared. But remember, since I is the square root of negative 1, then I squared must be negative 1. So when I do that 4i times negative 3i, I get negative 12 times I squared, which is negative 12 times negative 1, which of course is positive 12. Everybody see that? Now I wrote these, you're looking at that going, yeah, but why did you put the 8i last even though you did that one first? This is 8i plus 12, but remember when we write a complex number, we normally write the real part of the number followed by the imaginary part. So once we do that, we're just about done. I mean, we've done what I said we needed to, which is we've written this 4i over 2i plus 4i over 2 plus 3i in a way where we don't have an I in the denominator. The only thing we need to do from there, so once we get to that point where we've got 12 plus 8i over 13, what you're going to find when you do the homework problems is that they will tell you to do this division problem and to state your answer in standard form for a complex number. And remember, standard form for a complex number is a plus bi. Some number plus some number times I. There's a real part A, an imaginary part B. So what they want you to do when you get here is they just want you to write this in standard form. So we would just say that that is 12/13 plus 8/13 I, like that. We just split it up into sort of two separate fractions. If you leave it like this and give this as your answer, they'll tell you that's incorrect and they'll remind you to state your answer in standard form for a complex number. By the way, what we've done here isn't any big deal. It's just like saying if I have 2 plus 3 all over 7, everybody agrees that's 5/7, right? Well, I could also write it as 2 over 7 plus 3 over 7. So you can split a fraction up like this. You just have to keep the entire denominator under each thing, right? So that's what we'll need to do. So let's look at one more of these. And this one is a little bit different because we've got complex numbers that aren't just imaginary on top and bottom. But what we do is the same. So we want to do 3 plus 5i divided by 6 plus 3i. So that denominator, 6 plus 3i, what do I need to multiply it times to get rid of the I there? Oh, come on.
6 minus 3i.
Did they say 6 minus 3i? Good. Yeah, I need to multiply it times its complex conjugate, 6 minus 3i. But don't forget, if I multiply the bottom times 6 minus 3i, I have to multiply the top times 6 minus 3i. In the denominator, again, if you wanted to FOIL this, completely distribute it and combine like parts, you could do that. But we know what's going to happen because these numbers are complex conjugates. We're going to square the first number, 6 squared, 6 times 6, that's 36. We're going to square the second number, 3 squared, 3 times 3, that's 9. We're going to add them together. 36 plus 9 is 45. So we know we're going to get 45 on bottom, and we know that that gets rid of the I in the denominator. On top, unfortunately, we don't get to use a shortcut because these are not complex conjugates, right? Here we have to actually do the multiplication. It's just foiling or distributing, however you think of it. So we're going to say that 3 times 6 is 18. 3 times negative 3i is negative 9i. 5i times 6 is positive 30i. And finally, 5i times negative 3i. Now, 5 times negative 3 is negative 15. I times I is I squared, which is really negative 1. So negative 15 times negative 1 is positive 15. So 5i times negative 3i is actually positive 15. Of course, here on top, we need to combine like parts. So 18 plus 15 is what, 33? And negative 9i plus 30i is positive 21i, is that right? And that's all over 45. And of course, we need to write this in standard form. And when we do, we'll have 33 over 45 plus 21 over 45 I. Now here's a question. Am I finished at this point? I got rid of the I in the denominator. I wrote it in standard form. Am I finished? I'm not. Why am I not? I'm not finished. Why am I not finished? Because we always simplify fractions if they can be simplified, right? And 33 is 3 times 11, and 45 is 3 times 15. I can cancel a 3, right? 3 goes into 33 11 times. 3 goes into 45 15 times. I think I can do a similar thing with the 21 over 45, can I? 3 goes into 21 7 times, and 3 goes into 45 15 times. So in the end, I actually get 11 over 15 plus 7 over 15 times I. And that's what I'm going to give as my final answer. Everybody see how to do this? So really, division problems kind of turn into multiplication problems if you think about it. Now, I claimed that we did a division problem, but do y'all see what I meant when I said that it won't ever feel like we're doing division? It'll just feel like we're, that we've got this rule that tells us what we have to do to call it simplified, and we've done that. But just to show you that we really have done division. Remember, anytime you do a division problem, and we're claiming that we just did, or I'm claiming, that we just divided 3 plus 5i by 6 plus 3i. And I'm claiming that when we did that division problem, we got 11 over 15 plus 7 over 15i as our answer. Remember that if we really did a division problem and did it correctly, we can show that. We can prove that we've done a division problem, and we can prove that this is the correct answer to that division problem. We would need to multiply our divisor, 6 plus 3i, the thing that we were dividing by, times our quotient, our answer. And if we've done a division problem and done it correctly, when we multiply these two things, we should get this dividend 3 plus 5i. Everybody see that? And we can actually check to see if we did. If we multiply 6 plus 3i, our divisor, times our quotient, 11 over 15 plus 7 over 15 times I. If we multiply these, we should get 3 plus 5i. So let's see what happens. When I do 6 times 11 over 15, well, that's 6 over 1 times 11 over 15. 6 times 11 is 66 over 1 times 15 is 15. So we get 66 over 15. Then we do 6 times 7 15ths I. Well, 6 times 7 is 42. So we're going to get plus 42 over 15i. Then we're going to do 3i. And 3i times 11 15ths, well, 3 times 11 is 33. So we're going to get plus 33 over 15i. And finally, when we do this last times last one, 3i times 7 15ths I, well, 3 times 7 is 21. So I'm going to get plus 21 over 15i squared, which is really minus 21 over 15. And when I combine like parts, 66 over 15 minus 21 over 15. 66 minus 21 is 45. So I get 45 over 15. And then when I add the imaginary parts, 42 plus 33 is that's 75. 42 plus 33 is 75. So I get plus 75 over 15 I. Well, 45 divided by 15 is 3, plus, isn't 75 divided by 15 5? So plus 5i. And that's what we're supposed to get. So we really did do a division problem. Y'all see? So the main thing to remember here is anytime you're dividing complex numbers, if I just go back here up to where we have this all sloppily done, but oh well. If you're dividing by 6 plus 3i, you need to multiply times 6 minus 3i. If we were dividing by 2 minus 5i, we'd need to multiply times 2 plus 5i. You know, you always multiply the denominator times its complex conjugate, which gives you a real number on bottom. But whatever that complex conjugate is, you also have to multiply the top times that complex conjugate. Then you just do the multiplication, combine like parts, split it apart into its real and imaginary parts. And of course, if these are fractions, check to see if you can simplify them, right? Everybody see this? So that's the whole process for dividing complex numbers. Okay. Section 1.5 is there's one specific type of equation that we're working on. In section 1.5, we're solving quadratic equations. And here in a few minutes, we'll look at exactly what we mean when we say an equation is quadratic. We're going to look at 3 different methods for solving these things. We're going to first look at how you can solve them by factoring. Then we're going to look at how we can use something called the square root property to solve quadratic equations. And finally, we're going to look at how we can use a formula called the quadratic formula to solve quadratic equations. These 3 methods are all fairly important. The quadratic formula is certainly important because it turns out that every single quadratic equation, and by this we mean one variable quadratic equation, every quadratic equation that only has one variable, every one in the universe can be solved using the quadratic formula. The square root property is important, first of all, because ultimately it's what led to the quadratic formula, but it's kind of important because if you have a quadratic equation in a certain sort of friendly form, the square root property gives you a really, really fast way to solve equations like that. Factoring is important because if the quadratic equation can be solved by factoring, usually if you practice your factoring skills a little bit and get pretty comfortable with it, it's faster and less prone to arithmetic mistakes than the quadratic formula. But anyway, we'll take a look at all of these methods. We'll see if we make it through all of them tonight or not. So the first thing we need to talk about is, and this is going to lead directly into this idea of solving quadratic equations by factoring. This has nothing in and of itself to do with quadratic equations. It's just arithmetic. And so we've got this little arithmetic rule, property, law, whatever we want to call it, that says that A times B is equal to 0 if and only if either A equals 0 or B equals 0, or both of them equal 0. That little thing it's simple. This is something all of us know, right? Like, we all know that 6 times 0 is 0, or 0 times 13 is 0, right? We all know that anytime we multiply 2 numbers, if at least one of the numbers we're multiplying is 0, we always get 0 when we do the multiplication, right? And it's also true, this sounds like the same thing, but it actually isn't. It's also true that anytime we multiply 2, so anytime we multiply 0 times any number, we'll get 0. It's also true that anytime we get 0 when we multiply 2 numbers, at least one of the numbers has to be 0. So if we multiply a number times 0, we'll always get 0. if we multiply two numbers and get 0, one of those numbers has to always be 0, right? That thing is called the zero product principle. The name doesn't particularly matter, but still, that's the name. The zero product principle. It just says if you multiply two numbers together, you'll get 0 if and only if one of the numbers you multiplied is, in fact, 0. So how can we use that? Well, what if we have an equation like this? These look a little goofy. They don't look like what we've been doing. But here's an equation. It says x times, in parentheses, x minus 3 equals 0. Now, another way of looking at that equation is I could say that's the equation x squared minus 3x equals 0. Do y'all agree that these are the same equation? Because all I did here is I distributed that x. Does everybody see? If you look at this version of it, it might not be easy to see the solution, or maybe it might not be easy to see both of the solutions because there are two solutions here. But if you look here, it should be really easy to see because we just saw that zero product principle that says anytime you multiply two things together, you'll get 0 if and only if one of the two things you multiplied was itself 0. Well, notice here I'm multiplying two things together. I'm multiplying x times x minus 3. So do you agree, y'all look where I'm pointing, if I replace this x with 0, do you agree that when I do the multiplication, I'm going to get 0? If I plug 0 in place of this x, by the way, if I plug 0 in place of this x, of course, I'd also have to plug 0 in here, right? Because that's x. But even if I did, 0 minus 3 is negative 3. If I plug 0 in for x, I'll have 0 times negative 3, and that's equal to 0, right? So this statement will be true if x is equal to 0, right? What if I plug 3 in place of x? Will the equation also be true? So I'd plug 3 in here, times, I'd plug 3 in here. Well, isn't that 0 also? We do what's in the parentheses first. 3 minus 3 is 0, right? And 3 times 0 is 0. Then these are the two solutions to that equation. Not one solution, but two. Or if that's still kind of rattling around in your brain, look at this next problem. What if I replace x with negative 2 in this equation here? Won't I get 0? I mean, negative 2 plus 2 means that number would be 0. Here, I think if I plug negative 2 into this factor, the 2x minus 1 factor, if I plug negative 2 in there, I think I get negative 5. Do y'all agree? 2 times negative 2 is negative 4. Negative 4 minus 1 is negative 5. But does that even matter? Because when I plug negative 2 in here, I got 0. And 0 times negative 5 is 0. Now, here's a question. What would I need to plug in place of x to make this second factor 0? The one that says 2x minus 1. What would I need to replace x with for that to be 0? Well, if you don't just look at it and see, think about this. So I need to know what value of x makes 2x minus 1 equal 0. Let me say that again. I need to know what value of x makes 2x minus 1 equal 0. Couldn't we just solve that equation to find out? So what would I do to solve this equation? Get x by itself? This is section 1.2, linear equations, right? Add 1 to each side. I get 2x equal 0 plus 1 is 1. And wouldn't I then just divide each side by 2? So we get 1/2. By the way, it's easy to see that that's true. If I plug 1/2 in here in place of x, does everybody see that 2 times 1/2 is 1 and 1 minus 1 is 0, right? Then those are the two solutions to this equation. This is an example of solving quadratic equation, or these are examples of solving quadratic equations by factoring. The only thing is, I had already done the factoring for you. Generally, that won't happen. So let's look at some quadratic equations. So first of all, when we say that an equation is quadratic, we mean that the highest degree variable term in the equation is second power. So remember in section 1.2, we were solving linear equations. A linear equation is one where the variable only ever shows up raised to the first power. With a quadratic equation, the highest degree variable term is always x to the second power. The reason we call them, I may have mentioned this, but the reason we call those quadratic, quad means 4, is because the highest degree variable term is the second degree or squared term, right? And the Greek word for square is quadros, meaning basically 4 regular or equal sides. So the highest degree term in a quadratic equation is the quadros or squared term. So these are quadratic equations. You have x to the second power. And so these are, I feel like, a little bit trickier than the linear equations to solve because, you know, some of those linear equations, I could just look at them and sort of know the answer. These, maybe it's not as easy to do that. What I need to be able to do is factor this thing, kind of make it look like this looks. Because we've seen that if we can make it look like this, if we can write it as 2 factors, then it's just figuring out what value of x makes each factor 0, and that gives us our solutions. So here it turns out that when you factor these, and some of you are probably good at factoring and already know how to do this. Some of you maybe used to be good at it and you've forgotten how to do it. And some of you may not ever have been great at this. So I'm going to try to show you the best way I can to give you the best chance to sort of learn to be reasonably good at this in a reasonable amount of time. It turns out that when you have this is called a quadratic trinomial. Again, quadratic meaning the highest degree variable term is x to the second power. Trinomial meaning it has 1, 2, 3 terms. Typically, in a quadratic trinomial, you're going to have a second degree variable term, a first degree variable term, and a constant term. It turns out that if a quadratic trinomial can be factored, and not all of them can, which is why we'll later need the quadratic formula. If a quadratic trinomial can be factored, it always factors as 2 first-degree binomials. In other words, each of these factors will have a first-degree x term and a constant term. And this one will have a first-degree x term and a constant term. And so it turns out there's a super easy way to figure out what those factors are. Because it turns out that whatever goes first here and here, the term that goes first in each set of parentheses, and the 2 sets of parentheses, those 2 terms have to multiply to give us this first term, x squared. So does everybody agree that the only thing in the universe that you can multiply, or the only pair of things you can multiply to get x squared is x times x, right? I mean, technically you could do 1 times x squared. There's other ways to do it too, but within reason, x times x is literally the definition of x squared. So we know when we look at this, we got to start with x and x. So we've already found 2 of the 4 terms that go in these 2 sets of parentheses. Now the numbers that go last, and they will be numbers, constants, They have to do two things, and y'all watch this real carefully because this is important. This is what makes the difference in whether you're going to be good at this or not so good at it. These two numbers have to do two things. First, when you multiply those two numbers, you have to get this last number, positive 12. Now that helps us because there's only a few pairs of numbers in the universe that multiply to be positive 12, right? But even more than that, these same two numbers, listen real carefully to this one, these same two numbers that have to multiply to give us positive 12 have to add to give us this middle number, which in this case is negative 8. So you might be thinking, well, they got to multiply. The two numbers have to multiply to be positive 12. Well, they can't have opposite signs. Do y'all agree? Because anytime you multiply positive times a negative or a negative times a positive, you always get a negative. It could be a positive times a positive, but don't forget they could also be a negative times a negative, right? That would also give you a positive number. So I know that these two numbers are both going to be negatives. Do y'all see why I know that? Because I know that they have to have the same sign, otherwise they won't multiply to be positive 12. But if you add two numbers with the same sign, you add the numbers and keep the sign. So in other words, if I were to add two positive numbers, I would get a positive number. The only way to add two numbers that have the same sign and get a negative answer is if both of them are negatives. And I am supposed to add them to get negative 8. So what are those two numbers? Yep. Does everybody see it would be negative 2 and negative 6? Negative 2 times negative 6 is positive 12. That's our last number. Negative 2 plus negative 6 is negative 8, and that's our middle number. Everybody see? Then I know this is factored correctly. And if you wanted to double check that, of course, you could FOIL it out and combine the like terms to see that you get x squared minus 8x plus 12, but you will. So then what are the two solutions to this equation? I think we need a light bulb moment here. 2 and 6, I agree. Why? Because if I replace x with 2 in this first factor becomes 0. If I replace x with 6 in this second factor, 6 minus 6 is 0, so the second factor becomes 0. And you may be thinking, well, yeah, but if you replace this first factor with in this first factor, if you replace x with 2, you get 0, but when you replace x here with 2, you don't get 0. It doesn't matter because 0 times whatever number this is 0, and that's a true statement, right? And when I plug 6 into this second factor, it doesn't matter what I do, what happens when I plug 6 into the first factor, because it's going to be that number times 0, which is 0, and that's a true statement. So again, once when you've got it set equal to 0 like this, if you can factor this quadratic trinomial, you figure out what makes each of those factors 0, and that gives you, in this case, your two solutions to the equation. Everybody see that? Incidentally, remember when we were solving those things like 2x plus 1 equals 7, where we had those linear equations where we only had x to the first power? Seemed like we were always getting exactly one solution, right? And that was a first degree equation. Now we've got a second degree equation. It looks like we're getting two solutions. Everybody see that? That is not a coincidence. You can expect in general when you solve quadratic equations, you're going to come up with two solutions. There's kind of a little disclaimer on that, but I'll try to show you an example in a bit to show you what that disclaimer is. Okay, so let's look at this one. Now this problem would be kind of similar to the other one, except notice the other one was a quadratic trinomial on the left and 0 by itself on the right. Before I do anything else to this equation, I need to subtract 24 on each side first. So in other words, when you solve quadratic equations, generally you want them to be set equal to 0. Why do we want to do that? Because we want to be able to take care of that, take advantage of that zero product principle that says if I can factor this thing, as long as I have 0 on the other side, all I have to do is figure out what makes each thing equal to 0. Well, see, I can always make this look like something equals 0 because we know, for instance, if I want to subtract 24 on this right side to make it 0, there's nothing wrong with doing that as long as I subtract 24 on the left side as well. Does everybody see that? So when I do, I'm going to get x squared plus 5x minus 24 equals, of course, 24 minus 24 is 0, and that's what we wanted to do. We wanted it set equal to 0. Now I'm going to try to factor this. And remember, if I can get it factored, because I've got that thing equal to 0, all I have to do is figure out what makes each factor equal to 0. Okay, so I know I have to start with x and x because x times x is the only way to get x squared, right? Remember, these last two numbers have to multiply to be negative 24. So are the two numbers going to both be positive? Are they both going to be negative, or are they going to be one of each? One of each. They have to be because they multiply to be a negative number, negative 24. The only way to multiply two numbers and get a negative is if the two numbers have opposite signs. So one number's positive, the other's negative. Now, here's the thing you got to remember on problems like this one. Remember that these same two numbers that multiply to be negative 24 have to add to be positive 5. But when we do this in this problem, when we add these, we're going to be adding two numbers that have opposite signs. But when you add numbers with opposite signs, what do you really do? Well, let's do it and see what we did. What if we had so here I'm adding the negative number, negative 11, and the positive number, positive 3. What do I get for my answer? Y'all are scaring me. Do we need our calculator? I mean, use it if you need it, but we probably ought to be able to figure this one out. If you have negative $11 in your checking account, but you deposit $3, how much do you have in your checking account now? I figured poor starving college students would know this immediately. They must be better off college students than I was back in the day. I could have told you right away that I would now have negative $8 in my checking account. And I mean, if you need a calculator, use it, but y'all really should work to get your arithmetic skills on point. It makes a huge difference in how you do, but the point is negative 11 plus 3. If I owe the bank $11 and I give them 3 of those dollars, don't I now owe them $8? Okay, it's negative 8, right? But what did I do to get that? This is a plus symbol, so are we doing what we think of as addition? Because evidently 11 take away 3 is 8, right? So evidently what we did is we did subtraction and then we kept the sign of whichever number was bigger. In other words, 11 is bigger than 3, so we kept the sign that goes with 11, which is the negative sign. Everybody with me there? So when you add numbers with opposite signs, and this is where many of you, and I shouldn't get on this tangent, I'll try not to stay on it long, but I should say this. Many students get damaged while learning elementary school math. It's because we teach you that addition is this one thing and subtraction is this separate thing that we learn to do. We teach you this. By the way, I don't teach kids that. I would never teach elementary school math because they would make me teach kids that and I couldn't look at myself in the mirror. We teach you that addition and subtraction are these two totally separate things because we're lying to you about something even more important, which is 0 is not the smallest number in the universe, right? When you were a kid, they have not introduced you to the idea that a number can be smaller than 0. You don't know about negative numbers. I don't know where they're getting to it now, but you know, probably in the old days around 5th grade or maybe 6th, just before you hit pre-algebra, it would be better if we just taught you, look, a number can be bigger than 0, it can be smaller than 0, but there's just basic rules of arithmetic, and here's the basic rules. If you did this, instead of negative 11 plus 3, if you did negative 11 minus 3, what's that equal to? Negative what? Negative 14. Now, you were taught in 1st and 2nd grade that that is a subtract or minus or take away symbol, right? But this is the correct answer. Did we do to accomplish negative 11 minus 3? Did we actually perform the operation that we think of as subtraction? Didn't we actually add? I mean, where does a 14 come from? Well, we must have done 11 plus 3. We did. These are both negative numbers. This isn't a subtraction problem. It's a signed addition problem. This is a signed addition problem. And so is this, and so is this. Subtraction and addition aren't two separate things. They're two separate parts of the same thing. Signed addition. And so signed addition says anytime you add two numbers with the same sign, you add the numbers and keep the sign. So this is positive 2 and positive 3, right? We add those and we get 5. It's positive 5 because both these numbers are positive. We added the numbers and kept the sign. This is negative 11 minus 3. This is just an addition problem. We're adding the numbers negative 11 and negative 3. They have the same sign. So I add the numbers to get 14. I keep the sign, well, then it's negative 14. Do y'all see that? Those are both signed addition problems. This is also a signed addition problem, even though the answer we get is negative 8, which somewhere in there must have required us to do what we think of as subtraction. But actually, the rule just says if you add two numbers with opposite signs, you subtract the numbers. In other words, just ignore their signs and do the subtraction. 11 take away 3 is 8. Then you keep the sign of whichever number is bigger. And by that, we mean an absolute value. But it's just easier to think of it like the signs are opposites, negative and positive. So I subtract. I just do 11 take away 3 is 8. Then I look at the numbers. 11 is bigger than 3. I'm ignoring the signs. 11 is bigger than 3. That means I need to keep the sign that goes with the 11, which is the negative sign. Everybody see that? See, here's 1st grade subtraction. It's actually the exact same problem as this one. This is positive 11. This is negative 3. The signs are opposites. So I do subtraction. 11 take away 3 is 8. I keep the sign of the bigger number. Well, 11 is bigger than 3 and it's positive, so my answer is positive 8. Y'all see? So you can know everything there was about addition, including the part of it that they taught you to think of as a separate thing called subtraction. You could have learned it all in the 1st grade if they just told you these two simple rules, even if you don't really know exactly what negative numbers are. You know, when you learn the alphabet, you don't exactly know what that is either, but you really didn't know that to figure out how to read later on with it. But anyhow, it is what it is. So were we doing a problem in there somewhere or something? I can't even remember at this point. Oh, yeah, this one. So, okay. Let me try to reset. So we have subtracted 24 on each side to set it equal to 0, and we have done rocket science to figure out that we have to start with x and x because x times x is the only way to get x squared. Then we figured out that these two numbers have to have opposite signs because they multiply to be not 24 but negative 24. Now we know that these same two numbers have to add to be the middle number. which is positive 5. But this long, drawn-out discussion we just had, I apologize for that. What we found out is adding these two numbers is really going to involve what we think of as subtraction, right? So you could think of it like, what two numbers can we subtract to get 5? So what are the numbers? Say again? Positive 8 and negative 3. So Audrey's saying it's positive 8 and negative 3. I agree with her, by the way. And here's one other thing to think about. She's already got ahead of me on this, but I want to make sure y'all see this. If I know that I'm going to subtract these numbers and keep the sign of the bigger number, do y'all agree that when you look here, it tells you right away that the bigger of our two numbers is going to have to be the positive one? Because we're supposed to keep the positive sign, so the bigger number has to be positive. So now we're just looking at what two numbers multiply to be 24 that subtract to be 5, and definitely that's 8 and 3, right? And we know that the 8 has to be positive and the 3 has to be negative, right? Because, and of course easy to check, positive 8 times negative 3 is negative 24, check. 8 plus negative 3 is literally just 8 minus 3, which is positive 5. So that's factored correctly. X squared plus 5x minus 24 is the same thing as x plus 8 times x minus 3. So what are the two solutions to the equation then? Speak up a little more. Well, if I plug 8 in here, 8 plus 8 is 16. Don't you want it to be 0? Negative 8. And then what should this one be then? Positive 3. I agree. So notice what goes here to make, what you plug in here to make this 0 isn't 8, it's negative 8, right? Because remember, our rule says that if you add two numbers together and get 0, that's only going to happen if they're the same number but with opposite signs. So if this is positive 8, that means I need to plug negative 8 in to make it 0. And this is negative 3, that means I need to plug positive 3 in to make it 0. Everybody see that? And so these are our solutions. By the way, if we go back to the original equation, even before I set it equal to 0, remember it was x squared plus 5x equals 24. And remember, when we say the solution set are the numbers negative 8 and positive 3, we're claiming that each of these numbers makes not just this statement true, but this original statement true, right? And so just quickly, we'll do one of these just to show you that it does, but you can always check your work. Let's try negative 8 because it looks like the one that's the most weird one of the two. So if I wanted to check my solution here, I would just need to replace x in this equation with negative 8. I would have negative 8 squared plus 5 times negative 8. And of course, I would need to know, is that equal to 24? Well, negative 8 squared means negative 8 times negative 8, and that is positive 64. And then positive 5 times negative 8, isn't that negative 40? And I get 64 minus 40 equals 24. And of course, 64 minus 40 is equal to 24. That's a true statement. 24 is equal to 24. So negative 8 really is a solution to that original equation. Everybody see that? And if you did the same thing with 3, I'll just kind of walk through it real quick. If you plug 3 in for x, you'll get 3 squared is 9. Here you'll get 5 times 3 is 15. So you'll have 9 plus 15, which is also 24. Those are both, in fact, solutions to the original equation. Everybody see how this goes? All right. It's about 3 minutes till 7. We're going to try to do just a couple more. Then we're going to take our break. Let's take a look at this one. Now, this one's a long way. I mean, it's got two terms on the side opposite the x squared term. Y'all see that? Remember, we always want it to look like something equals 0 when we start solving these quadratic equations. So What I'm going to do is I'm just going to subtract 4x on both sides, and I'm going to subtract 12 on both sides. I mean, technically, you could subtract x squared on both sides. That would give you 0 equals negative x squared plus 4x plus 12. There's nothing wrong with that. But you're always going to want your x squared term to be positive. So if you did that, you'd have to multiply both sides times -1, and so on. It's probably just easier to say, look, if it's not set equal to 0, just move all the terms to whichever side of the equation the x squared term is on. So that's what I'm going to do. I'm going to subtract 4x on each side, and I'm going to do two things at once. I'm going to also subtract 12 on each side. Now make sure you follow this and see what I'm doing, because sometimes I see students try to do this and they make a mistake. First of all, do you agree that on the right-hand side, I'm definitely going to get 0? I mean, that's the whole point. 4x minus 4x is 0, and 12 minus 12 is 0, so I just get 0. I'll see students, y'all look where I'm pointing, I'll see students try to put these together. Do you see why you can't put those together? They're not like terms. This is x squared, this is just x. So I'm just going to have x squared minus 4x minus 12. X squared minus 4x minus 12 equals 0. Now it looks like the ones we've been doing. And so we want to factor this thing. Well, I mean, the only way to get x squared is to start with x and x. You can kind of see if that first term is just x squared, these things always they always come down to figuring out the numbers that go last. Okay, like the last problem, does everybody agree that those numbers have to have opposite signs? And do you see why? Because they got to multiply to be -12. Now they got to add to be -4. So what are the numbers? They have opposite signs, remember.
-6, +2.
That will do it. -6 and +2. So here's what she noticed. They have to add to be -4, but since they have opposite signs, they have to be two numbers that multiply to be 12, but subtract to be 4. Obviously, that's 6 and 2, right? Then to figure out the signs, all you need to know is we're not supposed to get +4, we're supposed to get -4. We know that when we subtract, we keep the sign of the bigger number, so we knew that the bigger number had to be a negative. So it's +2 and -6. So what are the two solutions? -2 and +6, I agree. Let me say one more thing about this one, then we're going to do one more problem and take a break. When you solve this equation, it would have been okay if you had written x minus 6 times x plus 2 equals 0. Do y'all see that these two factorizations are the same? It doesn't matter what order, the factors are written in, right? I mean, if you do that, what are you going to get for your two solutions here? +6 and -2. Oh, +6, -2. That's the same thing we got here, right? Because that would be just like if I said 21 is 3 times 7, well, you might have been thinking in your head 21 is 7 times 3, but that's not wrong, right? They're the same thing. Here's what would have been wrong. Do you see why that would be wrong? Because that is not correct. That's the correct way to factor x squared plus 4x minus 12. And if you factored it this way, you'd get +2 and -6 for your solutions, right? But those aren't the solutions. It's -2 and +6. So the point I'm making is the signs here really matter. But which factor goes first and which factor goes second does not matter. Everybody with me? I just mention that because sometimes students get nervous because I'll do a problem in class and they'll think, oh, well, now I'm scared because what if that problem's on a test, and when I do it, what if I get x minus 6 times x plus 2? Is that going to mess me up? No, if they're the same factors, right? And again, you could always plug these numbers back into the original equation and check your work, right? Okay, let's do one more, then we'll take our break. So x squared plus 10x plus 21 equals 0. This one's already set equal to 0 for you. So you just got to factor and figure out what makes the factor 0. And of course, we know that. We're not even talking about the x and x anymore because that's obvious. So everybody take a minute and just see if you can figure it out. Give everybody a chance to work on it a minute, and then we'll see if y'all got that. Remember to think about, the signs on those terms and what that means. Am I really the only one that's hot in here? I'm dying. Bailey, are you not hot? Oh, dear God, I'm burning up. Kobe, you think you got it? What'd you get for those two numbers? Positive, both positive? He says it's x plus 7 times x plus 3. Do y'all agree that that works? And again, quick way to check it, right? I mean, we know that x times x is giving us x squared. We just need to check, is 7 times 3 equal to positive 21? Yes, it is. Is 7 plus 3 equal to the middle number, positive 10? Yes, it is. And so notice he figured out that both numbers had to have the same sign because they multiply to be positive 21. But this time they both need to be positive numbers because they add to be positive 10. So what are the two solutions then? I mean, we've got it factored, so what are the solutions to the equation? Yeah, -7 and -3. Because -7 plus 7, that -7 makes the first factor 0. -3 plus 3, -3 makes the second factor 0. Those are the solutions to the equation. Everybody good there? All right, let's take a break. I've got to figure out a way to cool off. I may have to actually go outside to cool off. All right, so let's take a break. I am going to put us on mute here in Greenville just so we're not bugging. And we'll start back at about, I don't know, 7, what time is it now? About 7:08? 7:20. Let's say 7:20, we'll get rolling again.